So these two are physical questions. So that is the trend in the earlier papers, because now the trend is different in new syllabus. The organic question will be in part C, and part B you have 3 physical question, which is necessarily you have to do 2. So you need to know about your physical chemistry as well, right? So we will start the discussion. So please go through, if you think this is too much for your mind, please go through the video slowly and you try to understand each part by part. Okay, each things, all the things part by part. Okay, so we will move on to question number 5. Okay, so question number 5. So you have given the first question that A and B are volatile compounds, completely miscible, and it forms an ideal solution. So typically, you have an ideal solution where you have A and B. Okay, according to the Raoult's law. A mixture containing 1 mole of A and 1 mole of B. So you have 1 mole initially, 1 mole initially of A and B. And this is a closed container, okay. And when the system reach equilibrium, the pressure, volume, and of the gas phase and the molar ratio in this phase were found to be. So they are not talking about the gas phase. They have given the gas phase pressure. The total pressure is 10 to the power 5, I guess. Yeah, 10 to the power 3 Pascal. And they have given the volume. It is 0.8314 m cube. And they have given the molar ratio between A and B. So Na, Nb is 2:3. So these are the details that they have given. And the temperature is given as 200 Kelvin. Okay. Calculate the following. The total number of moles in the gas phase. Okay, so you need to first find Nt. What is Nt? And mole fractions of A and B in the liquid phase. So you need to find XA liquid and XB liquid. Second, saturated vapor pressure. So you need to find what is it? P0A, not PA. So you need to find the saturated vapor pressure, P0A and P0B. Okay. So the question is clear because you have given all the information that you need to find. Now we will go through slowly how to determine. So first thing is Nt in the gas phase, right? So in the gas phase, you can see total pressure is given, volume is given, temperature is given. So you know R as well. Then you need to use ideal gas equation. Pressure is 10 to the power 3. Remember, you need to put everything using units. You need to put units. That is the important thing. And volume is 0.8314. Nt, R is 8.314. Temperature is 200. So according to this, you can calculate this. It is easy because you have given the same thing that you can use to cut. So typically, here if I cut this one and this one, it's like yeah, so typically this will be 0.1. 0.1 into 10 to the power 3 means 10 to the power 2. So typically I can cut this 2 for 10 to the power 2 to 10 to the power 2. So Nt will be 1 over 2. So Nt will be 0.5 moles. Okay, Nt will be 0.5 moles. This is the total number of molecules. 0.5 moles, total number of moles. This is one way. Then in the second question, what they are asking is, what is XA liquid and XB liquid at the equilibrium? Because initially they used 1 mole of A and 1 mole of B. So what is going to happen? What is going to happen here? A will be in its equilibrium with A gas and B will be in equilibrium with B gas, which means if you have 1 mole of A here initially, some amount of X will be now in the gas phase. And in the same way, if you have 1 mole of B initially, some amount of Y will be in the gas phase. So in the liquid phase, the amount that will remain here is 1 minus X. And in the same way, the amount of B that is remaining in the gas phase will be 1 minus Y. Why? Because initially they have used 1 mole. So if you know this X and Y, number of moles, you can find the number of moles that is present in the liquid phase, and then you can find mole fraction. So first thing, you need to find the number of moles in the gas phase. So how do you find? To make your life easier, the first question is given. What is it? Find the total number of moles in the gas phase. Because now you know NT in gas phase is 0.5 moles. And they have given the mole fraction of A to B in the gas phase is 2:3, which means you can calculate Na is what? The ratio A is to B, this ratio is 2:3. So what you have to do? You have to get 0.5 and the component of A is 2 and the total component is 5. That is how you calculate number of moles from a ratio, right? 2:3. This is O level max. So you have 2, which gives the contribution for A. So in the same way, 0.5 is the total number of moles, contribution 3 over total contribution. So typically you can understand the amount of moles of A in the gas phase is 0.2 moles and the amount of B in the gas phase is 0.3 mole. So you can see 0.2, 0.3, 0.5 moles, the total number of moles. So now you the number of moles of A and number of moles of B in the gas phase, which means here you have 0.2 moles and here B you have 0.3 moles. So what is the amount of moles that is remaining in the liquid phase? Here it is 1 minus 0.2 mole, which is 0.8 moles of A. And here it is 1 minus 0.3, which means you have 0.7 moles of B in the liquid phase. So that is straightforward. But this is not what they are asking. They are asking about the mole fraction of A and B in the liquid phase. So you have to go one step further. So what is one step further? XA liquid is the number of moles of A, 0.8, or total number of 0.8 plus 0.7 is 1.5. So in the same way, XD liquid, 0.7 over 1.5. So this is what they are asking. Okay, you don't need to like divide this and put 0 point something. It is actually not necessary, but if you want, you can put. Okay. So we are done with NT, this one and this one. And finally, what you have to find here is saturated vapor pressure, P0A and P0B. So how do you find that? How to find? So always I told you when you do these questions belongs to Raoult's law and this ideal solution, we always use two equations, right? One is Raoult's law equation, the other one is Dalton's law equation. So think about the Dalton's law, and I told you we always put the Dalton's law to the vapor phase and Raoult's law to the liquid phase. Okay, so in the vapor phase, we have an equation like this. PA should be equal to XA gas PT and PB should be equal to XB gas PT. This is according to Dalton's law. In the liquid phase, we should have PA is equal to P0A XA liquid and PB is equal to P naught B XB liquid. Okay, and these two are same because saturated vapor pressure cannot be changed, right? These two are same. The only thing is we use here Dalton's law to calculate the vapor pressure, and here we use the Raoult's law to calculate vapor pressure. That is the only difference. Okay, so according to this, here you know PT, here you know XA gas that we already found, right? And then you can calculate PA. In the vapor phase, according to Dalton's law, you know the total pressure, which is 10 to the power 3, and you know XA because we calculated XA using this mole fraction. One of the moles is 0.2, one of the other mole is 0.3, so one will be 2/5, the other one will be 3/5 mole fraction. So you know this one. In the same way, you know PT and XB and you know PB. So which means you know PA and PB. So if you know PA and PB and you know XA liquid and XB liquid, which we calculated here, which is this one and this one. The only thing that you don't know here is this. Okay. So when you want to calculate this one, you can first find PA, then PB, and you can plug this here to find P naught A and P naught B. But it will take some time to calculate PA, PB and plug here and divide. So rather than doing that one, you can automatically write these four equations, and you can write equation 1 is equal to equation 3 and equation 2 is equal to equation 4. And you can just equalize this equation to this equation to this equation and find P naught A directly. Because it will give some more space, more time allocated for you to do other questions. Otherwise, if you do this separately, like finding PA and PB, and it will take some time. Okay, so you're allocating time for the question itself, not for you. Okay, so this is the entire question here. So I will share this. Okay, so we found first the total number of moles, and we found the mole fractions in the liquid phase, and finally we found the saturated vapor pressure. So saturated vapor pressure, how do you find? You use these equations to find it. That is the easiest way to do it. Okay, so the first part is done, and the second part, so you have given another nice question, I would say, because this is a very nice question. In fact, this counters all your acid base equilibrium as well as solubility product as well. Okay, so we will go through this question as well. So I hope this part is clear, because this is always very straightforward questions. So the only thing is you always have to use Dalton law or Raoult's law. Okay, so I will share the screen for myself. So in a saturated solution of MnOH2 ice at 25 degrees, the concentration of Mn2 plus is given, right? So let's say we have a saturated solution. So here Mn2 plus concentration is given as 10 to the power 5 m. And they have given the Ksp of MgOH2 ice as 10 to the power minus 10 m cube, and they are talking about Kb of NH4OH as 1.6 10 to the power minus 5 mLDM minus 3. Okay, so we have a solution, saturated solution of Mn2 plus, and now they are asking calculate the solubility product of MnOH2 ice, right? So this is a saturated solution of MnOH2 ice. That is what they have given. So if you think about a saturated solution, it is always in an equilibrium, right? Because that is the limited or the minimum point to form the precipitate. Because if you have a solution that is saturated, you have maximum amount of MnOH2 that you have dissolved in the solution, because any additional amount of MnOH twice to the solution will be precipitated out. So that is the idea. Okay, so what you have to do here, if you want to calculate the MnOH solubility product, you have given the Mn2 plus concentration as well. So the idea is, in a saturated solution, you will have this equilibrium. Mn2 plus 2OH minus aqueous. Okay. So in this saturated solution, they have given the concentration of Mn2 plus, that is 10 to the power 5 m. So if you know this as 10 to the power 5 m, this will be twice of it. So this is 1 into 10 to the power 5, and this should be 2 into 10 to the power 5 m. Okay, because in this equilibrium, when 1 mole of MnOH is dissociated, it will give 1 mole of Mn2 plus and 2 moles of OH minus. So the concentration should be double according to this piece of information that they have given. Right? Then you can write Ksp MnOH twice is equal to Mn2 plus aqueous concentration times OH minus aqueous concentration to the power 2. Why to the power 2? Because stoichiometry is 2. Then you know the concentration of Mn2 plus, that is 10 to the power 5 m minus 5 m. And here it will be 2 into 10 to the power 5 m to the power 2. So typically this will be 4 into 10 to the power minus 5 into 10 to the power minus 10. So this is 4 into 10 to the power minus 15 cube. Okay, so this is the idea. So when we discuss about solubility product, we discuss in three different ways, many different ways. One of the ways is like, if you have given the solubility, we try to calculate the solubility product. So the first question belongs to that. You have given the solubility of Mn2 plus this one and this one, you can automatically calculate it, and you can back calculate the Ksp value. Okay, so this is first question. So you can calculate solubility product. Then the second question tells, calculate the concentration of hydroxide ions in a 0.01 m NH4OH solution. So the idea is, you have given 0.01 m NH4OH solution. Right, so you have given 0.01 m NH4OH. So you have 0.01 m NH4OH solution, and you have given Kb as 1.6 into 10 to the power minus 5. Okay, so again you need to think about its equilibrium. So if you remember about the equilibrium, it was like this: NH4 plus OH minus, right? So you know the concentration, so you can take this as 0.01 initially, and finally this will be 0.1 minus x. X is the dissociated amount, so this will be x and x. So according to the Kb equation, so NH4 plus OH minus concentration over NH4 OH concentration. So you know 1.6 into 10 to the power minus 5. So this can be, you can take an as x squared over 0.01 minus x, you can take as 0.01, by considering dissociation x is very small. So this will be 0.01. So based on that, this x squared will be 1.6 into 10 to the power minus 7. So I can put this as 16 into 10 to the power minus 8. So I can directly take the square root. So this will be 4 and minus 8 square root will be minus 4. So the concentration of NH4 plus is 4 into 10 to the power minus 4, as well as OH minus concentration is 10 to the power 4 into 10 to the power minus 4. So in the first equation, the first question, we use the solubility to collect solubility product. Second one, we use Kb to find the concentration of OH minus in this type of a solution. But remember, there is no connection between the first question and second question. Because first question, they are talking about a separate solution. In the second question, they are talking about a separate solution. That's it. Right? Now, we will go to the second question and third part as well. Okay. So first one is done, second one is done. Okay. Now we will come to the third one. Determine the concentration of NH4OH necessary to start precipitate MnOH2 from 0.001 m solution of MnSO4. So first we will draw and then we will discuss. Right? So the idea is you have to find the amount of NH4OH that is necessary to precipitate manganese hydroxide. That is the idea, right? So there is a solution here and you have given the concentration that is 0.001 m. Okay, and this solution is MnSO4. That is the idea, right? And you need to put NH4OH some amount so that in the solution MnOH twice solute is precipitated. This is the idea. Okay, and they are asking determine the concentration for this particular thing. And we know the manganese hydroxide KSP we already found. It was I think I have to check now. I don't remember this. Let's see, where is it? I will quickly check the KSP value which I calculated just before because I don't remember now. Yeah, 4 into 10 to the power minus 15. That is what we obtained, right? 4 into 10 to the power minus 15, right? So this is the KSP of MnOH twice. So now try to understand this clearly, right? Right. You have a MnSO4 solution. The concentration is given. That is one part. The other thing is you have to add NH4OH to this solution to form this precipitate. So the first thing is you can argue to form this precipitate, what should be the minimum concentration of OH minus that should be present in this solution? Because you know the concentration of Mn2 plus. So if you know the concentration of Mn2 plus, you should know the concentration of OH minus using this KSP value. Okay, but you should be careful. Why? Because this OH minus that is necessary to get precipitate MnOH twice is given by ammonium hydroxide, not by sodium hydroxide, because sodium hydroxide completely dissociate to give all OH minus, but ammonium hydroxide will be in its equilibrium like this. Okay, this OH minus concentration you can find using this KSP and manganese 2 plus concentration, because that is the amount that is needed, the minimum amount that is needed to precipitate. But in the question, they are asking about concentration of this one, not this one. They are asking amount of NH4OH, concentration of NH4OH that you should use to precipitate out, right? The first thing is to find the minimum OH minus concentration that is necessary in order to precipitate manganese hydroxide. So again, you can use Ksp of MnOH twice is equal to Mn2 plus concentration, OH minus aqueous concentration, solid up to the power. So you know this one, 4 into 10 to the power minus 15. And you know here Mn2 plus, it is 0.001 means 10 to the power minus 3 times OH minus aqueous concentration to the power 2. So typically I can divide this 2. This is 10 to the power minus 3. So this will become 4 into 10 to the power minus 12. So 4 into 10 to the power minus 12 is equal to OH minus squared. So OH minus concentration is 2 into 10 to the power minus 6 m. Okay. So now as a first point, I have found what is the minimum amount of OH minus concentration that is necessary in order to form this precipitate. That is 2 into 10 to the power minus 6 m. That is done. The second thing is, if you know this concentration, this will be the concentration here. 2 into 10 to the power minus 6 m, which is formed after the dissociation. So if you think NH4OH initial concentration is C and the final concentration is C minus X, this should be X and this should be X, and this X which is finally in the solution should be equal to 2 into 10 to the power minus 6. Why? Because initially you can think the concentration of NH4OH is C, but after the equilibrium there should be a concentration in the solution which will allow you to precipitate this manganese hydroxide. So we used Ksp value of manganese hydroxide to find how much OH minus should be there. That is this amount. And after the dissociation of NH4OH, so this amount of concentration should be there. So if you know this one, which means you know this one as well, it should be also 2 into 10 to the power minus 6. And here you know your Kb value, 1.6 into 10 to the power minus 5. So the only thing that you don't know is this initial concentration C, which they are asking. So typically you can write Kb is equal to 2 into 10 to the power minus 6 times 2 into 10 to the power minus 6, because these two concentration are we know, and this one will be divided by C minus X. And still we can tell the dissociation X is very small. So you can still take this as C. So your C will be 4 into 10 to the power minus 12 over Kb, which is 1.6 into 10 to the power minus 5. So you can find how much concentration, what is the concentration of ammonium hydroxide that you should add into the solution to get this precipitate happening. Okay, so did you understand this? Just say yes or no. I see 2 people here. Okay. Did you get this? Okay, what about Seema? Did you get this? Okay, so that is very nice. The idea is clear, I guess, right? So you have to precipitate this out, but you have to precipitate using ammonium hydroxide. That is our problem. So here first we use Ksp value of this to calculate how much OH minus you need. But you know this OH minus is not the OH minus that is completely from NH4OH. Okay, it is from the dissociation, after the dissociation. So this OH minus should be equal to this one, which means NH4OH, the concentration should be a little higher than that actually, right? Because of the dissociation. So then we use this Kb value to calculate the initial concentration of NH4OH we should add. Okay. So that is the idea of this third question. So I will share it again. Where is it? So this is the idea of here. Determine the concentration of NH4OH. So this is done. Right. Then question number 4. If 5.35 grams of NH4Cl is dissolved in 1 decimeter of 1 m NH4OH. Calculate the concentration of hydroxide ions in the solution. So typically here it is a case of the Kb, same Kb, but they are asking about a common ion effect, right? So if I draw again the picture, so what they are going to do here, they have a solution like this, and so we have 1 decimeter of this, and the concentration of ammonium hydroxide is 1 m. Yeah, it is 1 m, and you are putting here 5.35 grams of ammonium chloride. Okay, and they are asking about the final OH minus concentration in the solution. So still here, remember, there is no connection with the other questions, right? So we will see what is going to happen here. So I will stop share and use the board again. Right, it's nice. Okay, so what is here in the solution? That is one thing. So we have initially the NH4OH equilibrium. So there will be NH4OH equilibrium. Okay, and its concentration is also given, that is 1 m. Now what you are going to do here is you add a little bit of NH4Cl. So NH4Cl is a salt, right? So it will give you NH4 plus and Cl minus, and you are adding 5.35 grams to the solution. So you can find the concentration of NH4 plus in the solution. So if you think about the molecular weights, so here this is nitrogen is 14, hydrogen is 4, this is 35.5. So in fact, if you think this is 53.5, so 5.35 over 53.5 grams per mole. So it is like 0.1 mole, right? So 0.1 mole in 1 decimeter means 0.1 MOLDM minus 3 is the concentration of NH4 plus. Okay, because 0.1 mole divided by 1 decimeter. So this is the concentration of NH4 plus in the medium, which means now there is an effect to this equilibrium by NH4 plus. Why? This NH4 plus will act here, increases the concentration of NH4 plus in the medium, and which is not good. Why? If you increase the concentration of NH4OH in the medium, according to Le Chatelier's principle, still they have to maintain this Kb, because Kb is a temperature dependent constant. This equilibrium should favor to the left hand side, which means the reversible backward reaction happens more, and here the equilibrium will be shifted towards NH4OH, and now OH minus concentration will be reduced. Why? Backward reaction happens more. Okay, which gives the idea the OH minus concentration in the presence of an ammonium chloride solution. When you add a little bit of ammonium chloride, what is happening? The concentration of OH minus is decreasing. Okay, so if you think the concentration of OH minus is decreasing, why it happens? Because of the common ion effect of NH4 plus. Okay, so now for this particular equilibrium, now we have to put the Kb equation to get the concentration of OH minus. Here we know the initial concentration C, that is 1 m, and finally this should be C minus X, this should be X, and this should be X. But this should not be alone X, because we have added little bit of ammonium chloride, and it will give this amount of concentration in the solution. That is the common ion. So here when you put the concentration of NH4 plus, it should be X plus 0.1 m. This one. And still X is little bit smaller, which means this X plus 0.1 you can write down as 0.1 m. Because dissociation X is very small. Now you know the Kb equation. So Kb is 1.6 into 10 to the power minus 5. Concentration of NH4 plus is 0.1 m. Concentration of OH minus is X. So I will put it as X. Instead of X, I will put as OH minus concentration. This one. And divide by 1 minus X. So 1 minus X is still 1. Because if I take 0.1 plus X 0.1, this 1 is very large. So 1 minus X is still 1. So this will be 1. So typically in the solution, your OH minus concentration is 1.6 10 to the power minus 5 over 0.1 m. Okay. Yeah, so this should be your answer. 10 to the power minus 5, 10 to the power minus 4. Okay. This is your idea. Right, so what we have done, first we have done the amount of ammonium chloride that we added. Using this one, we can find the number of moles of ammonium plus in the solution. So it will be 0.1 m in the solution. Then we think about our equilibrium reaction. So typically, if you consider about this equilibrium, here we can get the initial concentration that they have given as 1 m ammonium hydroxide. So after the dissociation, this could be 1 m minus X. So this should be 1 m minus X. And here this should be X plus 0.1 m. Why X plus 0.1 m? Because this is the common ion effect of the NH4 plus. So here it is X, right? So you can use the Kb equation to find the concentration of OH minus. So give me a second. Yeah, it is for 1.6 where I have to think just to check to make sure everything is fine. Okay. So it is 1.6 into 10 to the power minus 4. Yes, that is correct. So last one. Right? So this is a common ion effect. So you can understand how much detail that you have here. First, we calculate the solubility product of MnOH, then using the KSP concept, then we use hydroxide using KB concept, then we use the solubility product, one of the concept of precipitation, and then here we use common ion effect in the KB equation. So you see there is a diverse number of cases that they tested here. Okay, so this is very important to understand, right? So question number 5, calculate the number of moles of solid NH4Cl required to prevent. So before going to question number 5, I will come directly to question number 6 because this directly belongs to our description that just we have described the question, the calculation. Explain the use of ammonium chloride in group analysis. So if you watch my cation analysis video, I also have told this in that video also. In the group analysis, in the second group, after we add H2S and those things to precipitate all the sulfides, in the third, so I will show you here. Where is it? 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 Yes, I have. So I will show you. I will share the screen again. So this is our group analysis and flame test. So here, I will zoom out a little bit. Okay. Here you can see, right? So here, after from the filter rate from the group 2, after precipitation of all these sulfides, we come here, we add little bit of diluted HNO3, because if you have some amount of Fe2 plus in the solution, first thing that we do is we need to oxidize it to Fe3 plus. That is why we add diluted HNO3, and then we add ammonium hydroxide with ammonium chloride. The reason why we add ammonium chloride along with ammonium hydroxide in group analysis is to make the concentration of OH minus minimum. Okay, because when you keep the concentration of OH minus minimum, only the precipitates with low Ksp values will be precipitated. For an example, ferric hydroxide, chromic hydroxide, and aluminium hydroxide. These three, Ksp is very low. So if you have very few OH minus concentration in the solution, the ionic product of these precipitate quickly surpasses the Ksp because Ksp values are small. Okay, but there can be some other cations that can be precipitate as these hydroxides if you does not put ammonium chloride along with ammonium hydroxide. The common example is magnesium. So if you just put here ammonium hydroxide to this particular solution, this filtrate, this magnesium 2 plus will be precipitated as magnesium hydroxide, because if you don't put ammonium chloride, there will be higher OH minus concentration in the solution, which here even magnesium hydroxide ionic product will surpass its Ksp value to precipitate as magnesium hydroxide. But if you have ammonium chloride like this, which makes sense because it will reduce the ammonium hydroxide, the OH minus concentration will be reduced according to this one, right? Here you can see the OH minus concentration is reduced because of ammonium plus, right? So based on that information, if you have ammonium chloride in the mixture here, the precipitation of magnesium hydroxide is prevented. Why? Because when you do all these group analysis, right, magnesium should be found from here. Magnesium phosphate. This is the idea. This is where we find magnesium after group 5. And after group 5, the filter rate is taken to the flame test. So if you do the precipitation of magnesium here, there will be no magnesium in the group 5. That is 1 point. The other thing is magnesium hydroxide also will be white in color. So it will interfere with this aluminium hydroxide because it is also white gelatinous, right? So you can see here, I have explained this here. See, ammonium chloride will be dissociating from ammonium plus. So when ammonium plus concentration increases, OH minus concentration decreases because of the equilibrium that is shifting towards the left hand side. Okay, so I am telling again and again, go through this and you can understand. So what is the use here? So the question asks, what is the usage of ammonium chloride in group analysis? So the use of ammonium chloride in group analysis is to decrease the concentration of OH minus in group 3 to avoid the precipitation of magnesium ions as magnesium hydroxide. So that is the main use. Okay, so you have to know that one as well, typically, because if you have high concentration, not even magnesium, some other element also can precipitate out. That's the idea. Okay, so now we will quickly come to question number 5. So I will just use the board again to first write down what they have told, and then we will discuss very quickly. Okay. Right, so now we have a solution, let's say. So we need to calculate ammonium chloride, solid ammonium chloride. Prevent the precipitation of magnesium hydroxide. So this is what we discussed now, just before the group analysis. So we add ammonium chloride to prevent the precipitation of magnesium hydroxide. In a solution made by mixing 0.5 N, so we have a solution that is mixed with MgNO3 twice. The concentration is given 0.02 M. Is it 0.02 M or 0.2 M? So 0.02 M MgNO3 0.5 decimeter, and we mix ammonium hydroxide. Yeah, ammonium hydroxide. How much? 0.2 M. This is also 0.5 decimeter, right? So we mix these two and it will form magnesium hydroxide precipitate. And now they are asking how much ammonium chloride should be put here to prevent the precipitation of magnesium hydroxide. Okay. And if you remember the magnesium hydroxide, the KSP is given 10 to the power minus 10 MQ. I guess, yeah, 10 to the power minus 10 MQ. I will stop sharing so that I can see the board as well. So the situation is clear. You mix these two. So the total volume will be 1 decimeter. Since the volume is double of each, the final concentration of MgNO3 should be 0.01 M, and here it should be 0.1 M. Why? Because volume, when you add these two, it get doubles. So the concentration becomes half. Or either you can calculate 0.02 M is the concentration, the volume is 0.5 M, and 1 decimeter is the number of moles divided by total volume. So typically it is 0.01. Okay. So you have two data. What are the two data? You know the final magnesium nitrate concentration and you know final ammonium hydroxide concentration. Okay. And in the solution, first thing that you can do here is whether using these two concentration, you can check whether this precipitation actually happening or not. How do you check? You can calculate the ionic product basically. Because for magnesium 2 plus concentration, you can directly take this as 0.01 because this will be magnesium 2 plus and 2NO3 minus. So basically the concentration of MgNO3 will be equal to concentration of Mg2 plus. Okay, so this will be typically the Mg2 plus concentration, right? And here ammonium hydroxide, if you have 0.1 M, you can calculate what is the concentration of OH minus in the solution itself, because you can use Kb to find the OH minus concentration in the solution, and then you can find the ionic product to calculate the ionic product of magnesium hydroxide, and then you compare whether this is greater than this KSP value, and if that is greater than KSP value, surely this precipitate is forming. But for this question to answer, that is not necessary. You know why? Because it is already precipitating. That is what they are expecting. One thing that we have to do here is you need to prevent. How you are going to prevent? You are going to add ammonium chloride. That is the idea. Okay. So like the previous case, right? You can again think here in your favor. What is it? To prevent magnesium hydroxide solid, okay, it should be less than or equal to the Ksp of 10 to the power minus 10. Right? You can argue in two ways. I have explained this to you before also. If you want to precipitate, you can tell the ionic product should be greater than or equal to Ksp. If you want to prevent, the ionic product should be less than or equal to Ksp. So the idea is clear, right? So what you can do here, first thing that you can do here is you find the amount of OH minus that is necessarily needed in this medium to prevent the precipitation of magnesium hydroxide, because you know the Ksp value. Okay, you know the magnesium 2 plus concentration, so you can find to prevent the precipitation how much OH minus concentration you need. So you can tell, so to prevent the precipitation, Ksp MgOH twice solid should be less, or is it less or greater? Think about that little. Ksp should be greater than or equal to the ionic product, that is magnesium 2 plus OH minus Aq squared. So you know this. You know this. What is it? It is 10 to the power minus 10. You know magnesium 2 plus, that is this concentration, 10 to the power minus 2. And you need OH minus concentration squared. And you can find the OH minus concentration is 10 to the power minus 4m. Because 10 to the power 10 divided by 10 to the power minus 2 is 10 to the power minus 8. And you need to get the square root, that is 10 to the power minus 4. Okay. So up to this, it is clear. What is the method to prevent the precipitation of this thing, magnesium hydroxide? We need to look how much OH minus should be there in the solution. So we have calculated using Ksp and magnesium 2 plus concentration. This amount should be there. Okay. This is one thing that you need to do first. Right. Now, what you have to do here is, in order to get this OH minus concentration from this 0.1 ammonium hydroxide concentration, you need to calculate what is the NH4 plus concentration in this equilibrium. Because this is the equilibrium that we have. Okay, and we know the initial concentration of this. This is 0.1 m. Okay, and after a certain equilibrium, this will be 0.1 minus x, and this will be x, and this will be x. That's it. That's the idea, right? But we know, in order to prevent this precipitation, we know how much OH minus should be present in the solution. So that is 10 to the power minus 4. So this amount of 10 to the power minus 4 should be given in this solution after the addition of NH4Cl to the solution. So according to that, this x should be 10 to the power minus 4m, because that is the amount that should be present in the solution in order to prevent, right? So this one will be then 10 to the power minus 4 plus something, because we add NH4Cl. So we don't know the amount of NH4Cl that is added. So typically, this is 0.1 m minus x. So if you know this 10 to the power minus 4, the concentration, you know Kb, you just forget about this and you find the amount of NH4 plus that you should add. Okay, because if you put here 10 to the power minus 4 plus some x value, again we say what? The dissociation of x, which means this 10 to the power minus 4 is small. So we get the concentration of NH4 plus as the amount that is added. Like the previous case, we just took 0.1 plus x as 0.1. So now you know the OH minus, you know 0.1 minus x is 0.1, you know Kb, and you can calculate NH4 plus concentration that should be present in the solution. So if you know the NH4 plus concentration in the solution, which means you know the amount of NH4 plus in this 1 decimeter, which will be equal to its number of moles. Then if you know the number of moles, you can multiply by the molecular weight, 53.5 grams per mole, to calculate the amount of ammonium chloride that you should put into the solution.